Real numbers. Okay, so we can move on to our exercises. That is our first exercise in this chapter. Use Euclid's division algorithm to find the HCF of 135 and 225, 196 and 38220, 867 and 255. So let us look on our first example, that is 135 and 225 here. So at first we have to check which is the greater number among this. You can see the 225 is greatest, so we can choose 225 as our dividend and 135 as our divisor in the stage. Then by applying algorithm 225 greater than 135, by applying Euclid's algorithm, by applying Euclid division lemma to these two numbers, we could see that root 25 equal to 135 into 1 plus 90. You can do it by mind calculation or either by division method. 225 equal to 135 into 1 plus 90, 0 less than or equal to 90 less than 135. Okay, then here the 90 is our remainder and it is not equal to 0. Then what next? We have to apply the Euclid's algorithm again by taking 135 as our dividend and 90 as our divisor. Okay, what is 135 equal to? 135 equal to 90 into 1 plus 45. 0 less than or equal to 45 less than 90. So again we got our remainder as a non-zero number and again we have to apply this lemma, then 90 equal to 45 into 2 plus 0. Okay. Then here we got our remainder as 0. So what is our HCF? HCF is divisor in the stage. What is our divisor in this stage? Which is 45. Hence, HCF of 135 and 225 equals to 45. Okay, let us move on to next problem. That is 196 and 38220. Here 38220 is greater than 196. By applying Euclid's algorithm again, here it is better to do the division method because the mind calculation becomes a tedious process. So, take 38220 as our dividend and 196 as our divisor. How much is 196 to 382? It is not completely divisible. So 1 times 196 it can be used here. That is, by taking 1 we will get 196 here, and now by subtracting, what is that? 6 will come here and 17 will come here, 8 will come here, 3 and 2 minus 1, 1. Okay, that is 1862. Then we are taking 2 here for continuing our process. Then what is 1862 according to 196? That is somewhat equal to 9. Okay, because 196 into 10 will become 1960. So we can choose 9 here. Then 196 into 9 will give 1764. Okay. Again by subtracting we will get, that is 9, 8. That is 12 minus 4, 8. Then here we have 15. 15 minus 6, 9. Here 7. 7 minus 7, 0. 1980. What is 980 according to 196? It is 196 into 5. So we can take 5 here. Then we will get our remainder 0. So it is quite easy. single step we can find our HCF here. That is 38220 equal to 196 into 195 plus 0. What is our HCF? Divisor in this stage. What is divisor? 196. So HCF equal to 196. So let us move on to next problem. It is also an easy problem. So we have to find the HCF of 867 and 255. Then 867 is greater than 255 by applying algorithm. Here we can use the mind calculation, that is 255 into 255 into 3 will be our quotient, because 255 to 4 will give a number greater than 867. That is, we will get 9 in the third place by multiplying it by 4. So we can choose it as 255 into 3. That is 867 equal to 255 into 3 plus 102. That is it's equal to 0 less than or equal to 255 less than 0 less than or equal to 102 less than 255. So here we got our dividend as 255 and the divisor will become 102, hence since the remainder not equal to 0. So R not equal to 0 and 255 equal to 102 into 2 plus 51. What is 102 into 2? 204 plus 51 will give 255. Here also we got our remainder a non-zero number. Again we have to apply the algorithm or lemma by taking 102 as our dividend. Then 102 equal to 51 into 2 plus 0. So what is our HCF is divisor in this stage, that is 51. Okay, so we got our HCF of 51. So moving on to next. Show that any positive odd integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5 where q is some integer. So we have to prove any positive odd integer can be written in the form 6q plus 1, 6q plus 3 or 6q plus 5. So for that, take a be an odd positive integer. Then we have to prove a equal to 6q plus 1 or a equal to 6q plus 3 or a equal to 6q plus 5. So here by the previous knowledge we can see that, or we can find that we have to apply the Euclid division lemma to a and 6 to proceed this problem further. Okay, so it is in the form of the division lemma, that is 6q plus r. We have to apply the lemma to a and 6. So by applying Euclid's lemma to a and 6, we can write a equal to 6q plus r. If a and 6 are two positive integers, then a equal to 6q plus r, 0 less than or equal to r less than 6. So what are the possibilities of remainder? R equal to 0, r equal to 1, r equal to 2, r equal to 3, 4, 5. Okay, then the possibilities are 0, 1, 2, 3, 4 and 5. Then there are 6 possibilities of A2. Okay, but we have to eliminate all other possibilities. That is, if r equal to 0, we will get a equal to 6q, r equal to 1, 6q plus 1, r equal to 2, 6q plus 2, etc. Then we have to eliminate all other possibilities except these 3. Okay. So we have to eliminate the all possibility. Okay, we have to eliminate all the possibilities related to the r equal to 0, r equal to 2 and r equal to 4. So for eliminating, let us have a look what will happen when r equal to 0. Then if r equal to 0, then a equal to r equal to 0 means a equal to 6q, which is equal to 2 into 3q. Okay, what will happen when r equal to 2? Then a equal to 6q plus 2, that by taking 2 outside we will get 2 into 3q plus 1. Then when r equal to 4, a equal to 6q plus 4, by taking 2 outside we will get 3q plus 2. So these are the three possibilities when r equal to 0 to 4, and by observing these three numbers, that is these three values of a, we can see that they are multiples of 2. What is the problem with multiples of 2 and positive odd integers? Every multiple of 2 is an even integer. So these possibilities show that a is an even integer if r equal to 0 to 4. That is, for example, if 1 is an odd integer, by multiplying by 2 we will get an even integer. By multiplying any integer, that is 3 into 2 6, 2 into 2 4, then 5 into 2 10. As like that, by multiplying by 2 we will get the final result as a positive even integer. So these three possibilities are not possible here, since it is given that a is a positive odd integer. So in these three cases, a is a multiple of 2, hence it is a even integer for r equal to 0 to 4. Hence only three possibilities for a as an odd integers are a equal to 6q plus 1, a equal to 6q plus 3 and a equal to 6q plus 5. Hence we proved. So we have our problem here. An army contingent of 616 members is to march behind an army band of 32 members in a parade. The two groups are to march in same number of columns. What is the maximum number of columns in which they can march? Okay. So here we have a problem, that is, we have 616 army contingent members and 32 band members with us. We have to arrange them for a parade. How we have to arrange them? The two groups are to march in same number of columns. This will be considered for the arrangement. Okay. Then our duty is that to find what is the maximum number of columns in which they can march. Okay. We have to find that what is the maximum number of columns that we can arrange for the parade. Okay. So you have seen the march parade before that, how they are marching, that is army people, army band will be in front of army people and army people will march behind them very beautifully. So this will be in our mind if we before proceeding to this problem. Okay. Then here 32 members of army band and 616 army contingent members on behind the band have to march in same number of columns in a parade. Okay. That is, if band is marching at 2 columns, then army members have to march at 2 columns. Okay. Then we have to arrange them so that they can march in maximum number of columns. So our duty is to arrange them so that they can march in maximum number of columns. So we can have a look on three arrangements. That is, we can arrange them in a single column. Okay, that's 32 army band in a single column and 616 army members behind them in a single column. Or another arrangement is that we can arrange them in double columns. That is 32 members are arranged in double columns. Then we have 16 rows and 616 army members are arranged in double columns. We have 2 members each and 208 rows will be here. Okay. Then what happens when we arrange them in 3 columns? That is, in the 11th column of this army band, one last seat is vacant here. Okay, one last person is vacant here. Okay, person's position is vacant here. Then about 616 members, 2 positions are vacant here. Okay, this arrangement is not possible since you have seen how they are to march in same number of columns. That is, they have to march in same number of columns beautifully. This arrangement is not possible here. So how we can find the maximum number of columns in which they can march is that, for example, we can consider we have a 6 chocolate, okay, with us. Either you have to divide among members, okay, but the arrangement must be in equal number. Then with how many members you can divide your chocolate? That is, you can divide the chocolate with only one member by giving all the chocolate to him. Then among 2 members by giving 3, 3. Then among 3 members by giving 2, 2 equally. Then what about 4 members? Can we divide 6 chocolate for the 4 members? Okay, it is not possible. So what we have to look, in order to divide something equally, that thing must be the factor. That is, in order to divide 32 members in a column equally, that column number must be a factor of 32. Also, that column number must be a factor of 616. Otherwise, there will be a vacancy in the arrangement. So, what we have to find? We have to find a factor of 32 and 616 in order for our arrangement. Okay. Here one is a factor of both. No problem. Here we have 2. 2 is the factor of both. We have no problem. What about 3? 3 is not a factor. So we have to face a problem here. So we have to find the factor of both in order for this arrangement, and also here we have to find highest among them so that we can arrange them in maximum number of columns. So what we have to find here? We have to find HCF of 616 and 32 to find the arrangement here. Okay. For that we can apply Euclid's algorithm, that is 616 greater than 32. By applying Euclid's algorithm here, what will happen? Okay, we can do this by division method, or either you can proceed it by mind calculation. What will be the result here? 32 into 2 will be 640. Okay, that is somewhat 19 will be our quotient. We can check. That is 616, 32. Then 32 is 1 times in 616, that is 32. Then by subtracting we will get 29. We are taking 6 here. Then 32 is okay, it is 9 times in 296. If we take 296, then it is 288. Then what will be our remainder? 8. So by the arrangement we can write this in a Euclid division lemma form, that is 616 equal to 32 into 19 plus 8, 0 less than or equal to 8 less than 32. Here the remainder is non-zero number, so we have to repeat this lemma again by taking 32 as our dividend and 8 as our divisor. It is easy. That is 32 equal to 8 into 4 plus 0. Then what is our HCF? Divisor in this stage, that is 8. Then what is HCF? HCF of 616 and 32 equal to 8. Hence, we have to arrange them in 8 columns for the march. I hope it is clear. So here we have the next. Use Euclid division lemma to show that square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. So, here what we have to prove, if a is any positive integer, then a square equal to 3m or a square equal to 3m plus 1 for some integer m. This is our problem. Okay, let a be any positive integer, then we have to prove a square equal to 3m or a square equal to 3m plus 1. So, by having a look on this, we could say that 3m is of the form some 3q plus r. So, let us move on by applying the division lemma to a and 3. Let us proceed it and check whether we can find our answer or not. Okay. So, we are going to apply Euclid's division lemma on a and 3. Then what will happen? Then, hoping a greater than 3, then a equal to 3q plus r, 0 less than or equal to r less than 3, q any integer. Okay. So, this is our lemma. Then, here we have 3 possibilities for r, that is r equal to 0, r equal to 1 or r equal to 2. Then we have to check these 3 possibilities and to check whether we have a square equal to 3m or a square equal to 3m plus 1. So there are 3 possibilities for the remainder r and they are 0, 1 and 2. Case 1. If r equal to 0, then what is a? A equal to 3q. Then what is a square? 3q whole square, which is equal to 3 into 3q square, that is 9q square, which can be rewritten as 3 into 3q square, which is equal to 3m, where m equal to 3q square. Since we have m is any integer, we can choose m as 3q square, that is where m equal to 3q square, a square equal to 3m. So since we have to prove this, m can be any integer. So we are choosing, let m be 3q square in this case. Okay. Then we have our a square equal to 3m. Then what is second case? If r equal to 1, then a equal to 3q plus 1. Then what is a square? A square equal to 3q plus 1 whole square. Then which is equal to 9q square plus 6q plus 1. Okay. By expanding, we will get a 9q square means 3q whole square, 2 into 3q into 1, 6q plus 1 square will give 1. So, we have to check whether it is of the form 3m or 3m plus 1. Whether we can write it as the form 3m or 3m plus 1. By looking to this, we could see that a hope of writing this in 3m plus 1. How it is possible? 1, okay, this part is needed. What about this part? Can we take 3 outside from this part? Yeah. Then what will remain here? From these two, we are taking 3 outside. Then we will get 3q square plus 2q here plus 1. So we can choose this as our m. Since m is any integer, m can be this too. That is, which is equal to 3m plus 1, where m equal to 3q square plus 2q. Okay. Then what about case 3? If r equal to 2, then a equal to 3q plus 2. Again by squaring, a square equal to 3q plus 2 whole square Then expanding 9q square plus 12q plus 4. That is 12q, 2 into 3 into 2q. 2 into 3q into 2, that is 12q. Plus 2 square 4. Again, here we have 9q square plus 12q plus 4. Can we write this in this form, that is 3m or 3m plus 1? Okay, for that what we are going to do is, we are going to split 4 into 3 plus 1. Then what will happen? Which is equal to 9q square plus 12q plus 3 plus 1. Okay, these three members are multiples of 3. Okay, these three terms are multiples of 3. So we are taking 3 outside from this. Then, which is equal to 3 into 3q square plus 4q plus 1 plus 1. Since m can be any integer, we can choose these as our m, that is, which is equal to 3m plus 1, where m equal to 3q square plus 4q plus 1. Hence what we proved? Every square of a positive integer is of the form 3m or 3m plus 1. Okay. Hence, only two possibilities for square of an integer. A is a square equal to 3m or a square equal to 3m plus 1. So, moving on to our last problem. In this section, use Euclid division lemma to show that the cube of any positive integer is of the form 9m plus 1 or 9m plus 8. So what we have to show here, if a is any integer, then cube of a, that is a cube, is of the form 9m plus 1 or 9m plus 8, that is a cube equal to 9m or a cube equal to 9m plus 1 or a cube equal to 9m plus 8. For that, let a be any positive integer, then we have to prove a cube equal to 9m or a cube equal to 9m plus 1 or a cube equal to 9m plus 8, m be any integer. Okay, so since we have to prove a cube equal to 9m, that is 9m plus 1. So it is of the form sum a bq plus r, that is, usually we will apply Euclid division lemma to 9 and a in this case to observe whether we get this result or not. Usually we are going to do in such a manner. So there is a problem if we choose 9 as our divisor here. What is that? If we choose 9, there will be 9 reminders here. So we have to check 9 cases here. That is, what will be our reminder? When we apply Euclid division lemma to a and 9, a equal to 0, a equal to 1, 2, 3, 4, 5, 6, 7 and 8 equal to 8. So we have to check these 9 cases in order to prove this result. For simplifying our process, what we are going to do is, we are applying this lemma to a and 3. Okay. If you want, you can apply this lemma to a and 9 itself. Okay. For simplifying our process, we are applying this Euclid division lemma on a and 3. So why we are applying this lemma to a and 3? Why can't we apply on other integers? It's because when we take cube of 3, we will get a multiple of 9. Okay. So we can achieve this result as we take the divisor as 9. So by taking 3 cube itself, we will get a multiple of 9. If this result is held on by a positive integer a, we can prove it by taking this lemma on a and 3. Okay. So let us check whether we can achieve our result or not by taking this lemma on A and 3. This is our assumption that we can prove this result. Okay. Moving forward, if A and 3 are two positive integers, then A equal to 3q plus r, 0 less than r or equal to r less than 3, q be any integer. Okay. Then what are the possibilities of remainder? R equal to 0, R equal to 1 and R equal to 2. So we have to check these three cases for proving our result. Then case 1, if R equal to 0, then A equal to 3q. That is, by putting R equal to 0, we will get A equal to 3q. Then what is A cube? A cube equal to 3q whole cube, which is equal to 27q cube, which is equal to, by taking 9 outside, we can write it as 9 into 3q cube, that is 27q cube itself. Now by putting 3q cube equal to m, we will get a cube equal to 9m. So m is any integer, then m can be 3q cube also. Okay. Why it is so? Since q is any integer, q cube is an integer, 3 into that q cube will be an integer, so m can be 3q cube. Then case 2, if r equal to 1, then a equal to 3q plus 1. What is a cube? 3q plus 1 whole cube. Then by expanding it on the form a plus b whole cube. What is a plus b whole cube? A cube plus 3ab square plus a cube plus 3a square b plus 3ab square plus b cube. In that form we are expanding it, that is 3q whole cube plus 3q whole cube equal to 27q cube, 3 into 3q whole square into 1, that is 27q square. Then what is next? 3 into 3q into 1 square, that is 9q plus 1. Then now we have to change it in this form. So by observing these terms, there is a possibility of getting a cube equal to 9m plus 1. So for that, observe these three terms. 9 is common in these three terms. Okay. By taking 9 outside, we will get, from these three terms only, we are taking 9 outside, then we will get 9 into, by taking 9 outside, 3 will remain here. What will remain here? 3 itself, here 1 cube. Okay. Which is equal to 9 into 3 cube plus 3 cube square plus 9 cube, 3 plus cube plus 1. Then by taking these values as m, we will get 9m plus 1, where m equal to 3q cube plus 3q square plus q. Then moving on to next case. Case 3, if r equal to 2, then a equal to 3q plus 2. And what is 3q plus 2 whole cube? That is 3q whole cube, that is 27q cube. 3 into 3q whole square into 2, that is 27 into 2, that is 54q square. Then 3 into 3q into 4, that is 9 into 4, 36q, 2q, 8. Okay, this is an expansion. It is of the form 9m plus 8. Then for getting 9m plus 8, what we are going to do, we are taking 9 from these three terms outside, then we will get 9 into 3q cube plus 6q square plus 4q. That is, by taking 9 outside, 3 will remain here, here 6, here 4 plus 8. By taking these three terms as our m, we will get 9m plus 8, where m equal to 3q cube plus 6q square plus 4q. Okay? Hence, we got the three possibilities for cube of an integer a is a cube equal to 9m, a cube equal to 9m plus 1 or a cube equal to 9m plus 8. Hence we prove the result here.